We've got, let's see, nothing due today, quiz due on Wednesday. I have that we are finishing CFA this week. I find that highly unlikely that will actually happen. So I will see how far we get and update the syllabus as need be. I am waiting to put up homework 2 until I figure out how far we get today, because that will tell me whether or not I need to push the deadline back. So I will try to keep the deadlines such that you always have at least like 5 days in between things to make sure that whatever we finish, like you have time to actually implement. I'll tell you though that most of what homework 2 is about you already know how to do. It's just sort of the end parts that I'm waiting on to see how far we get. So I will let you know once that is available. So let's see, document recovery. Didn't realize something had crashed. So any questions, thoughts, things you want to talk about before we dive into a little review? No? We're good? Not the mama, what we're talking about here, CFA. So we started talking about what's in a CFA and what's it for. So let me give you a couple, let you stare at that for a bit. I'm going to call on folks. We're going to shake this up a little bit. Practice my names. How's that sound? Awful. Fair enough. Well, I'd like to hear from more than just a couple of you. Let's put it out that way. So I'll give you some softballs, and you can answer those first, right? And then you get credit for having answered a question, and I can't call on you again. Does that seem fair? Okay, so Hannah, what does confirmatory factor analysis, what are the letters that go with that? Very good. You're done. When I talk about CFA, what kind of model do I say it's the same thing as that you already know? Say, Heather, I'm going to call on you next. Regression, linear regression, right? Except that, what's the deal with the predictor? We're predicting the item response, and what is the predictor then? Yes, the two-parter. The factor, yes, very good. Give me all the names you can think of that go with factor as synonyms. Latent trait, there's one. Latent construct, there's another. Latent variable, yep. You've hit the world of, I'd say, SCM very well. There's also some measurement-y terms. Like the total score is a function of error plus true score, yep. Where true score is the mama and error is not the mama. We don't know what it is, we just know that it's not true score. And one more that we'll get to, as anyone had IRT, I'm going to call on Jihong for that. I know you have. Theta, yes, theta. So yes, all of those things mean the same thing. And what are, make it easy on you. Let me see, my PowerPoint doesn't want to show today for whatever reason. There it goes. Welcome back, PowerPoint. Yeah, it's like, haha, I'm not going to help you. It'll catch up eventually. What's in a measurement model? Let's keep working my way. Let's see, Euro, that's your turn. We're going to go front to back here. What's in a measurement model? That's one. Error of the item. Not exactly. You're thinking of the equation. So the measurement model has item parameters. You got two out of three. You got item intercept, item residual variance, and one more. Yep, he wants that one. Yes, slope or loading. Yes. Yeah, that's the thing that multiplies the factor. Yep. So item things are measurement model parameters. There's always 3 of those. Then what are structural model parameters? Okay, I'm going to finish out the front row. Emily, give me a structural model parameter.
So structural model is predictors.
Factor things. So 3 kinds of factor parameters we'll be interested in. She wants one. Factor variance? Factor mean, factor variance, and the other one? Covariance, yes. Covariance among the factors if there's more than one. Factor mean and factor variance. Very good. We talked about the first part of identification, which is setting a scale for the factor. So big picture, what does that mean when I say a factor needs a scale? More specifically, what does it mean?
We need to determine what the mean and the variance.
The mean and the variance, but you had your turn. We have to keep going back to the row. That's all right. I'm trying to get everybody to talk to me today. That's my goal. No worries, though. I appreciate the enthusiasm. Yes, we need a mean and a variance. There's two ways we can do it. There's the easy way, and then there's the more complicated way. What's the easy way? Yes, ma'am. Yes, you just set it to a number. Does it matter what the number is? Yes or no? No, it doesn't. It just needs to be, for a variance, something positive, right? If you try to set your variance to 0, that's not a great idea. A variance of -2, also not a great idea. But a variance of anything that's positive, A-okay. And what is the typical practice? Still your turn, Betsy. 1, yes. And typical practice for deciding what a factor mean is? 0. Yes, I didn't hear who said that. You're okay, now you're off the hook too. Yes. So I call that the z-score method because your factor is distributed as a z-score. So I know right away that the standard deviation is 1. That gives me a sense of if I tell you a factor score of -2, that means somebody who's not very high on this trait, right? They're pretty low at that level. What is the more convoluted way of setting a scale for my latent factor? Oh, I'm calling on you, Katie, because you've had this class before.
Fixing a marker item loading to 1?
Yes, picking one item and setting its loading to 1. Does it matter which item?
No, as long as it has a correlation to the factor.
As long as it measures the factor at all, you're in good shape, yes. And the analog to that on the other side of the model, what about the factor mean versus intercept? There's a convoluted way to set the scale of the factor mean by the same logic. Marker item.
Fixing a mean to 0?
Nope, that's the easy way. Convoluted way. Fixing something else to 0 instead.
Loading?
Nope, something else.
Variance? Fix the variance?
You could, but that's not where I'm going. Yeah, I told you it was convoluted. Who wants to help her?
What's the question?
The question is, what is the more convoluted way to set the scale of a factor mean? Meaning, don't just set the factor mean to 0. You got to fix something else to 0 instead. And it follows along the line as a marker item. Here, I'm going to have to figure out why my PowerPoint isn't working and open it again because I'm going to need the slides for this one. Let's see. Hey, it looks like it's working again. Hooray. I'm looking for, yes, yes. Tell us where you are here. Slide. Yep, there we are. So yes. So every latent factor needs a mean and a variance. Let me get to the next one where everything is side by side here. So along the top is what we've talked about so far. So top left, that's the easy way. The factor mean is 0, the factor variance is 1, the end. That means that you estimate all the item loadings, all the item intercepts, and all the item residual variances. The other way that Katie volunteered is the top right, where instead of saying the factor variance is 1, we say that one of the items has a loading of 1. The factor variance then becomes the part of that item's variance that's due to the trait. So if, let's say, I'm trying to do math in my head, always dangerous, but let's say that 75% of item 1 was due to the trait, then 75% of the variance in item 1 would become the number that that factor variance is. So if the item had a total variance of 12, and we know that 75% of it is due to true score, the factor variance would be 9. It would pick up whatever the good part of it is and become that number. The bottom ones then, no one would ever do this bottom left. This is just here for completeness. but the other one that you may see in the context of growth modeling, in particular longitudinal analysis, is when you let the factor mean get found as well by fixing one of the item's intercepts to 0. The factor mean then becomes the mean of that item. So on the bottom right here, you are completely borrowing a scale from one of the items. You're borrowing its intercept to become the factor mean, and you're borrowing its good factor variance, its mama factor variance, to become the factor variance up here. So M plus is default, and I think the default in most programs is the top right. And that is because that is the specification that we need once we move into SEM, where the factor is predicted by something. If this factor right here is to be predicted by other stuff, it needs to have a variance that can get reduced as a function of what's predicting it. It has to become a variance left over. And so it has to be an estimable quantity. So we're going to start out here on the left because this is easiest, it's hardest to mess up, and it's very straightforward to interpret the scale of the model. We will eventually have to move over here to the top right to where the factor variance is estimated instead. And I think for pretty much the entire unit except for one example, I think the factor mean will stay 0. We almost never need it to be an estimated quantity. Okay. With me so far? All right, who hasn't talked yet? Let's see. Adrian hasn't talked yet? Oh, it's right. You took an easy one. That's why I didn't even remember, because it was so beneath you. Let's see. Kahi talked? Yeah, you talked, or you're Kahi, I'm sorry. You are Weijin. Yes, I'm working on the accents. Amalari? Is that? Huh? Yeah, I thought I had it last time. Amirali. Okay, there. I got to think of a question for you. So when we talked a little bit about prediction and misfit, what is true so long as each item gets an intercept estimated? What is going to be true about the recovery of the item means? Perfect or not perfect? So data going in, parameters coming out. Let me find that slide here. This. So we're getting ready to do part 2 here on slide 18. Data going in versus parameters going out. So by data going in, we're actually talking about a summary of the data. We're talking about the item variance covariance matrix and their means. So we have as many means as we have items. If we let each item get its own intercept, the item means will be perfectly recovered because there's a 1-to-1 ratio in terms of data going in and parameter coming out. There's no room for misfit. The same is true for the item variances. If we let each item have its own residual variance, it picks up however much not the factor is left, and it becomes that number. It fills the hole in. So then this part, who hasn't talked yet? Have we got everybody? I think we got everybody. You haven't, oh, that's right, you showed up late. This is, you get the hard one here. So can you tell me what this means, this last bullet?
So item covariances going in.
I'll give you a hint. I kept saying the story is the covariance. The story is the covariance last time. That's what this means. Do you remember that? No?
So covariance is how much each one is varying from.
Covariance is how they vary together. So if item 1 is above the mean, is item 2 above the mean? That's a positive covariance. So covariance is a measure of relationship. So the job of the loadings. What are the loadings for? What do they predict? The covariance, exactly. So long as there are fewer loadings than covariances, That's where the misfit comes from. And that really is the whole point of this exercise. It's to see how well you can predict the pattern of covariance that exists in the data by the one that is coming from the model. So we have to be able to have enough information going in to estimate all the parameters, and then hopefully more than enough so that we can test the model. And that's where we're headed here, the second part of identification. Good. Okay. Questions or any of that you want to hear again? Yes, ma'am. To the extent that you have fewer factor loadings estimated than you have item covariances in the data, you have the opportunity to show misfit. So that's where there's fewer parameters being estimated than there are data points available to estimate them with. That's the story. Fewer parameters being estimated than there are pieces of data to estimate them with. The loadings come from the covariances. Other things you want to hear again? All right, so let's move on then. So we did identification part 1. Every latent variable needs a scale somehow. Now, CFA model identification part 2. This is the idea of whether or not your model is estimable in the first place, means can be figured out. You haven't overspent your degrees of freedom, so to speak. And then, is it testable? And this boils down to how many items you have. So we listed off earlier the number of parameters that are in the measurement model. Each item is going to get a factor loading, an intercept, and an error variance. We have factor variances and covariances and factor means. For each factor, 2 things are going to have to be fixed, something to set the mean and something to set the variance of the factor. How many possible parameters that you can estimate is given by this formula right here. So we're going to talk about the idea of data coming in and parameters going out, and the difference between them being something called degrees of freedom. You're used to thinking about degrees of freedom as a function of the number of people, like denominator degrees of freedom in an F-test or something. That ain't it. Degrees of freedom now is all about the number of items. So the total number of data points going into this analysis is given by this formula right here. It's the number of items times the number of items plus 1 divided by 2 plus the number of items again. So the first part of this is the variances and covariances. The plus V over here is to get the item means back in. So for instance, if I have 4 items, then I have 4 times 4 plus 1, that's 20, divided by 2, that's 10, plus 4 is 14. So the degrees of freedom then is the difference between the number of possible parameters, meaning how many data points you start with, minus how many you actually spent, estimated. And this degrees of freedom has to be 0 or positive for this to work. So here are some examples. There are 3 terms that describe different types of models with respect to identification: under, just, and over. Under-identified is bad. It's like you overdrew your checking account. So back at UNL, they used to deliberately oversell parking passes for certain kinds of lots. There were more passes sold than there were actual places to park, which meant that if you arrived at like 10 o'clock, you could walk forever and never find a lot, drive around and drive around. So I actually spent, I spent my money on the good parking, where the lot had just as many spaces as they had parking spaces, as many passes as they had spaces, so it was just identified. This is the same sort of idea here. Under-identified means that there is no way that this model can work. You are asking for too much relative to what you have to start with. And this happens when you try to estimate a basic CFA type model when you only have 2 items. So if we count the number of pieces of information going in, the answer is 5. We have 2 means, 2 variances, and 1 covariance. So we have 2 items. In setting up this model, if we go with the easy way of identification in the left column, 0 factor variances being estimated because we set that to 1, 0 factor means because we set that to 0. Then we're asking for 2 item loadings, 2 intercepts, and 2 error variances. We start out with 5 pieces of information. We're asking for 6 things. So the difference is -1. Means not solvable, not identified. Do not pass go, do not collect $200. The problem is that there are an infinite number of estimates, solutions, that would have the same fit. So here's an example from algebra. X plus y equals 7. That's not solvable. It could be 6 plus 1, it could be 3 plus 4, it could be 5 plus 2. There's not enough information to figure out exactly what x and y should be. So if we look at where the problem is specifically, each item has its own mean. Therefore, it can have its own intercept, 1 to 1. So the 2 item intercepts, not the problem. Likewise, each item has a variance to start with. Therefore, it could have its own error variance. That's not the problem. The problem comes in because there's only 1 covariance between these 2 things, yet we're asking for 2 loadings to describe that 1 covariance. So if I put this in correlation terms, this model would predict that the first loading times the second loading predicts the correlation between y1 and y2. If that correlation in the data were 0.64, then any of these combinations of loadings could recreate that 0.64 perfectly. There's no way we can know what the loading of 1 is separate from the loading of 2. Under-identified, broken. Does that make sense? So to fix this, the only thing that you can do that would help is to tell the model to make those 2 loadings equal to each other and have them estimate 1 number instead. So only this first option right here would be viable. In this situation, having a latent factor between these 2 is literally the same thing as just letting them be correlated. It's a semantic distinction. There's not enough information here to say how much of these items is due to the factor without assuming that they're both equally good measures of the factor. Okay. With me so far? So 2 items of 1 thing, not a great idea. How about 3? 3 sound better? Marginally. With 3, this is just identified, meaning that I've got 9 pieces of information I'm starting with. So once again, if we go through the list on the left here as the easier case, I'm fixing my factor variance to 1 for identification. I'm fixing my factor mean to 0 for identification. That's why they're not being estimated here. I've got 3 item intercepts. Those will perfectly take care of my 3 item means. I've got 3 residual variances. Those will perfectly fill in for my 3 original variances. And what I'm left with is 3 possible covariances among these 3 items, which are going to be perfectly taken care of by the 3 loadings. Degrees of freedom, 0. So this model is solvable in the sense that each of these parameters has a unique solution. But it's not testable in the sense that you've spent everything you possibly could, and there's no way to say how well it fits. It's just identified. It's just a rearrangement of the correlation matrix. It's not a model, it's just a description. There's no savings here. In your book, there's an appendix that I like that talks about how you can literally work through the math to do this yourself. If you start with the correlations among 3 items, the model tells you what they're predicted to be. So the correlation between Y1 and Y2 here should be A times B. You can figure that out for each of these. You can back solve for one of the letters and substitute in for the others, and then you can figure out what each of the loadings would be. So he works through this in the appendix of, I think, Chapter 4, and I thought this was fairly instructive to illustrate how there is a unique solution. It's just that it's not a useful one because there's no degrees of freedom left over. So 3 is the bare minimum that you need to make a factor. So how many do you think you need? 4. Yeah, question?
Yeah, so if ultimately you want to use another variable to predict your factor, why does it matter that you only have 3 so long as your factor has variance?
3 doesn't give you the capacity to say definitively that these items are measuring the same thing. It doesn't allow you to test whether you have a unidimensional construct. You just have to assume that you do and that your model perfectly represents it. So what you want is 4. And if you have 4, then you're in the good situation of being over-identified. Over-identified means you have not spent all possible degrees of freedom. You fit your model, you've got enough information to fit the model and find all the answers, but you still have some left with which to test its fit. So if we work through the math on this one, again, factor variance fixed to 1, factor mean fixed to 0, so there's none of those being estimated. I've got 4 item means, and my 4 intercepts cover those. I've got 4 item variances, and my 4 error variances fill in those perfectly. So where the story lies is that across these 4 items, there's 6 possible covariances, but there's only 4 loadings that are trying to predict them. So 6 covariances minus 4 loadings gives you 2 degrees of freedom left over. Okay, question? No? Okay. So really it's about the loadings. It's about the loadings and the covariances. I know the formula comes up with 14 because 14 comes from 4 variances, 4 means, and 6 covariances. But really it's the match of number of covariances to loadings. That's the thing that you have to care about. So now there's 2 degrees of freedom left over, and you can see how well your predicted covariance matrix matches the one in the data. And that's the basis of model fit. Okay. Questions? All right. So here is what can happen in reality. Let's say that you get an error message in your output where it says your model is not identified. Double check your starting values and blah, blah, blah. You will know that this happened because in addition to that error message, you will get no results. You will get a column of estimates without standard errors, without significance tests. If that happens, here are 2 situations in which this can happen, even if you think you've done everything correctly. Here's the first situation. It is technically possible for you to have 2 item factors and have the model be identified. If we count up the amount of information going in and information going out in terms of parameters, we're still at 14 going in. 4 variances, 4 means, 6 possible covariances. Fitting a 2-factor model would still use 1 intercept per item, so the means are fine. 1 residual variance per item, so the variances are fine. But now it is using 4 total loadings, so either a variance or a loading, one of the 2, plus a covariance to estimate the model. So this would be degrees of freedom 1 left over. Another way of thinking about this two-factor model is a one-factor model is saying that these two factors are completely, perfectly correlated, correlation of 1. The extent to which the correlation between these factors drops below 1 is evidence that you're measuring two things and not one. However, in this case, if the covariance was exactly 0, if these factors had nothing to do with each other, then each one by itself is under-identified still. So this is what's known as empirical under-identification, meaning you didn't screw it up, but the patterns in your data made it so your model's not identified, even though, in theory, this two-factor model is identified and each factor has a scale like it's supposed to. Here's another situation, and yes, I have seen this before. If you have 3 items, but one of them is terrible, has nothing to do with your trait, then functionally speaking, you have 2 items, not 3, and it's under-identified. So if you want to hedge your bets, let's say you're planning your dissertation, hypothetically speaking, right? And you want to know how many items I need. Well, let's go through this. Is 2 enough? No. Is 3 enough? It's enough for it to be solvable, but not enough for it to be testable. How many do I need for it to be solvable and testable? 4. What happens if one of them sucks? You're back at 3. So if you want solvable, testable, and room to have screwed something up, 5 at a minimum. However, 5 items may not give you good reliability. That's a whole separate concern. How well have you measured the factor? More items is almost always better, assuming that they actually are related to the trait. What's next? All right. So at the beginning of the semester, we compared and contrasted 2 different kinds of models. A reflective model, which is what we've been talking about, which is a factor model versus a component model. And here are those 2 pictures again. This is a formative model, stolen from your textbook. I apologize for the low quality here. But here's an example where we have 5 indicators, and they are pointing at the latent trait. This is what makes this different than what we're doing. These formative models, the arrows are going the wrong way. They're going from the item to the factor. The factor is the outcome, and the item is the predictor. So in the top model, that is not identified, because in addition to estimating all of those loadings, we still have to estimate all the covariances among the items. The factor is not in charge of predicting them with the loadings. The bottom picture is an example of a formative model that is identified because the author has brought in extra information. In this version of the model, we have X1, 2, and 3 that cause this bubble called chronic life stress. And that bubble itself is either a cause of or is measuring X4 and X5. Now this pattern of covariance allows the model to be identified. Now note that I hedged my bets in interpretation. From the bottom to the top, X1, X2, X3 are predictors that are causing this bubble called chronic life stress. From here, you can think of this as 2 ways, because the arrows are going out of life stress, out to X4 and X5. X4 and X5 are either outcomes of life stress, or they are observed variables measuring life stress. It's a semantic distinction. But the only way the model is identified is if you have extra information beyond what is supposed to be causing the factor. So you're not going to see these from here on out, because when you're interested in testing measurement, to me it makes no sense for it to not be identified unless you bring in a structural component, which is what these type of models require. So we're not doing formative measurement anymore. They're not identified by their own selves, as Huey would say. All right. So here's my intermediate summary. CFA is linear regression. The item responses are the outcomes. The factor is the predictor. The role of the model is to describe the pattern of covariance among the items with the item factor loadings. The factor loadings are what predict the covariance. We need at least 3 items to make this work. We need at least 4 items for a single factor to be testable. And the reason that this framework is useful, which we haven't talked a lot about yet, but this is coming later in the semester, is it offers greater potential to use the items in a way in which they were not necessarily intended. It separates the characteristics of the items from the characteristics of the sample taking them. So do you remember difficulty and discrimination in classical test theory? What's difficulty? What's item difficulty in classical test theory? Yeah, mean, right? Proportion passing, or the mean average? So if I have an item where 80% of my sample got it right, is that an easy item, or do I have smart people? Exactly. You can't separate that out. In what we're doing, item difficulty is not the mean. It's the intercept. The intercept is conditional. The intercept is the expected item response for someone with a trait score of 0. So if someone has a trait score of 0, that might mean that the factor mean is 0, and that's an average person. If the average person has an expected score of 4 out of 5, do you think that item's easy? I'd say so. If the average person has an expected score of 1 out of 5, is that item easy, or is that person smart? You start to be able to differentiate these things. So we're pulling apart the characteristics of the sample, the people, and the sample of items. And that means that we will be able to get comparable trait estimates regardless of whether or not each person took the same items. We're not adding items up anymore. There's no sum score here. That's gone. So when might people get different items? Well, one is if people don't cooperate. What happens if people don't want to answer certain questions? What do you do when you're creating sum scores? This has happened to you, right? Missing data? I know this has happened to you. What do you do? What do you do in your syntax to solve the problem of missing data? How do you create a sum score when people didn't answer every single item? You assign the value for the missing data, and then how do you compute the sum, though? Well, there's 2 things that you can do. In SPSS, directly as well as in other programs indirectly, you can say like sum.6, and that means it will only compute the sum if they had like 6 out of however many. Like you can give, and then the other way that people do it is to compute the mean instead, right? So if you compute the mean, then the mean is comparable even if not everybody answered every question. Well, by computing the mean, that implicitly assumes a type of mean imputation, that you're filling in the item mean for what the person didn't give you. Now, how likely is it that people skip items randomly as opposed to items that are either sensitive or difficult or they don't understand or some other characteristic of the item that's not random, right? So that's one thing that these models give you is the idea that you can have missing at random instead. The traits are supposed to be comparable even if not everybody answered every item, so long as their pattern of response is what's known as missing at random. And have you heard of the missing data stuff before? A little bit. There's 3 kinds. There's missing completely at random, which is exactly what it sounds like. That's what adding things up assumes. Missing at random means it's random after considering the rest of their data. It's a conditional random. So the idea is, as we'll talk about here in just a little bit, each person has some sort of multidimensional like mountain characterizing their data. And the idea is that any missing responses would not have altered the shape of that mountain. That's the idea, the big picture. So long as we know what they said to the rest of the items, and so long as we can put in person covariates as to why certain kinds of people might have not answered certain things, then you have a better shot at recovering more accurate inferences. And then the third one is missing not at random, in which you're just screwed no matter what you do, which is probably more realistic, but there's no statistical solution for that everyone can agree on, and that's why everyone pretends that doesn't exist. So in addition to people not cooperating, there are instances in which you may deliberately not give the same answers to people, or the same questions to people. If you're measuring abilities changing over time, right? You don't want to give 6th graders kindergarten math, and you don't want to give kindergartners 6th grade math. But if you want to measure math throughout elementary school, you have to give something that's comparable in order to assess change, right? So I see this a lot in the folks that I work with at the LSI here measure children's reading and pre-reading. And you might start with something like phonemic awareness, and then there's letter stuff, and then there's what, deletion? What is it? I'm making stuff up again. Someone help me. Yeah, decoding, that's another one. That's another word I know. Right, there's all these skills, and like eventually you get to reading, but you can't give 3-year-olds a reading test, and you can't give, hopefully, 2nd graders a test of do you know your alphabet, but somewhere between do you know your alphabet and can you read, you've got to fill in the gaps. The idea is that if you have overlap, at each point you give items measuring an early skill, the skill they're at, and the next skill. And as they grow, you swap them out for something harder, but you keep the overlap. Then you have a trait that can grow over time. But the overlap is the critical thing. If you give someone a test of alphabet knowledge and then 6 months later you give them phonemic awareness, you can't measure growth. You're screwed. It's all about the overlap. But with these types of models, given a concurrent calibration of kids of different ages with these different profiles, you can, in theory, link people back together with the same type of trait that's comparable across people and time, even if they didn't answer the same items. The same thing may be true in doing cross-cultural research. So I remember a presentation, a job talk I once heard. It was a woman from a Latin American country, and I forget which one, I'm very sorry. But she was talking about measuring parenting abilities, and there was a question in there about how often you give your kid time out. And she said the people in her study were like, what the hell is time out? Like, we have no idea what this means. Because apparently within this culture, within this subgroup she was examining, that just wasn't a thing. So that's an example of an item that would not be informative for this particular group and probably shouldn't be administered. If you can make a theoretical argument as to why certain items are relevant for certain kinds of people, then not everybody has to get all the items. So by separating the items and the people, it gives you a lot more flexibility in how you can customize your measurements for certain purposes. So this type of idea shows up all over the place in the world of IRT. It's almost never talked about in the context of CFA, but the same thing applies. It's the separation of items and people's abilities that allows you to do this. The fact that we have a factor score that is not just the sum score, that's what allows us to do that. There's my soapbox. Whew. Estimations next. Hooray. How are we doing, folks? You guys are looking a little sleepy today, I got to say. Should I take that personally, or is it just Monday? It's just Monday? Okay. Can you do me a favor and everybody stand up for like 30 seconds? And let's just like, okay? And I'm going to pull up something fun.